Okay, so let me start this last talk on some technical details. Not all technical details, but some of them maybe. I try to give you the main idea of what I understood. I don't think I understood all the subtleties of it, but so the setting was the following. We had a product of an abelian variety times anything, and then the domain sample jet space. We could write it like this, so it's trivial somehow, at least in the abelian variety direction. And we had this key player here, which were all the points in this guy here, such that we had some horizontal vectors which belong to the to this bundle here. And what I said is what Erwan pretty much explained in his talk, that this is always written as a product of something which is independent of K, and this guy so you have QK, which goes here to SK. Okay. And we were in the setting where XS, so the fiber of, so sorry, we had X in M, which was a closed subscheme. And we suppose that XS is different from A for all S in S. So that none of the fiber from this projection is actually the entire abelian variety. And so this will induce, so this, okay, this has nothing, any closed subscheme in M will induce the subscheme in K. Right? And so this has a projection, we'll write it PK. And to understand this map is one of the key tools in this study. So this is what is usually called the jet projection. And here what we study is the set of all S in SK, such that the Hilbert polynomial of the fiber XKS is equal to the maximal Hilbert polynomial of all the fibers. And so this is if XKS is non-empty, and it's just empty if XKS, if XK, sorry, if XK is empty. Okay. And so the lemma that I introduced last time was that there exists some stage star such that for any if P is a connected component of T mu on this space here. So just to emphasize, this is a subset in XK. There exists a proper abelian variety B in A, such that for any epsilon bigger than 0, there exists an open neighborhood U open in sk such that T is contained in U, and there exists some other constant rho such that you have this inequality. So let me write it like this: PD star of V A square omega A over B is less than epsilon. So let me emphasize here Vx A squared omega A plus rho Vx S mu omega S mu squared. Okay. And for any, that's a key point, in X in A times U, and for any Vx in V K V nu. So, and here PB, maybe just write. PB is a projection from A to A over B, and you have omega A over B, omega sk, which are positive 1-1 form. And I ask moreover that omega A and omega A over B are invariant. Okay, so just this is important just so that we can use the harmonicity, subharmonicity of the argument, which was explained by Erwan. And so here, let me just make a picture maybe. So we have A, we have SK, and so here, if we have a point here, X, and a vector Vx, which is here, then of course the projection here is what we write like this, and the projection down here is as a component in A. And so you can recover this guy best from this and this, just because the tangent space here is a product of tangent space. Okay, and so this is what I will try to explain. And so again, the point is that we want afterwards, we will integrate this equality. And the most important case, again, is suppose that B is trivial. Then this pretty much tells you that this is equal to this. And so that 1 minus epsilon times this is less than this guy here. And so, this guy here, because of some tautological inequality argument, will be bounded again by this guy here somehow. So this is where the argument comes from if B is trivial. And if B is not trivial, then you have to make some other estimates, which I will explain. And okay, and so let me give an idea of the proof. So there is a case which is simple. Suppose that you are suppose that T intersected with SK0 is actually empty. So let me draw this picture again. So you have your projection here, S nu. So here you have your S mu 0, and here you have, say, your T, something like this. And you look at the fiber here, and what you know is that all places where you have horizontal vectors are located above this guy here. Horizontal vectors in VK. So this means that here you never have a horizontal vector. All your vectors are somehow slanted. And so you can just say, okay, then I take a small neighborhood here, and over which, because all these vectors, so the idea is just to say that actually then Vk P nu As, the differential of this map here will be injective for all A, and let me write it like this. Injective in the neighborhood of T, and so then it's so the equality is then trivial. So you don't even have yes, it's trivial just because it's trivial. Okay, just some injectivity argument here. Gets the thing, and so it's somehow okay. And so the interesting case is if P intersected with S in 0 is different from P. So of course I didn't tell you yet what nu was, and for this argument you don't need nu. This works for any nu, wherever you don't T is not intersecting this. And so here you actually need to construct the V that appears here in the yeah, here I want to say that here yeah, maybe could have emphasized this, but here B is just the trivial abelian subvariety. So you just have to bound this guy by a multiple of this guy, and so which is trivial from this. And so if this is not empty, then we need actually a lemma, another lemma, which tells you the following. So under the same assumption as in this lemma here, there exists a nu bigger than 0, such that if T is a component, connected component of T nu, such that T intersected with S nu 0 is actually non-empty, then there exists B in A an abelian subvariety such that the intersection of this with this is actually included in S times, or I wrote it more like this, in times S. And so I recall here that this is included in BA times S, which is S 0. So this is where you can where this abelian subvariety comes from, and how do you actually conclude with the lemma? Is I case 2, so which is well, case 2 is this one, if we intersect this non-trivially. So you take mu as given by here. So and B as provided by the lemma. And as a second lemma somehow. And so you have B in A such that was included in P times S. And then what you have is that, so you have to think a bit about it. This will imply that for any A times S mu 0 of intersected with T, and for any Vx in V mu x, one has actually that actually T star of mu x of A is equal to 0 in A over B. So yeah, I guess you have to think a bit about it. It's somehow trivial once you realize that this somehow means that maybe Vx is not itself horizontal, but if you push it down one stage in the tower, then it will become horizontal, and it has also to lie in this times S, and this will actually say that this vector here actually is an element in B, and then of course it's sent to 0, and so this implies in particular that TB star of B B is equal to 0. So somehow this will tell you that here in the lemma, for all points which are in this guy here, this left-hand side here is actually equal to 0. And so this kills the trivial obstruction whenever this guy is non-zero, but Vx is actually a horizontal vector, then this will be equal to 0. And so then you would have some contradiction, right? Because this couldn't be arbitrarily close to 0. So this somehow kills this thing. And then basically you just have to do some, maybe I won't go into the detail, then it's just some topological argument to say, okay, then you can somehow compare whenever, say this guy is bigger than epsilon, and you compare, then it just the remaining is an exercise in topology. You just have to do some small estimate to hook up the proper open subset. Yeah. And okay, and so now we are now we have actually to prove this lemma here, which is the key, which is actually where you see somehow where abelian subvariety come from, and okay, so lemma comma. And so you take the first step is to actually construct nu. And to construct this, it's just that you have, so you have mk, which go to mk minus 1, etc. And inside you have mk0, minus 1, 0, and they are sent to each other as well. And now each of these is just a copy of themselves. And in this guy, you will have the different stages of the jet of the lift of x to the case of the jet space. And then what you obtain, and of course, it will be again sent onto each other. And so you get a decreasing sequence which is included, which contains the support of x1 times m10, which contains the support etc. And so then by notoriety, this will stabilize this. This will stabilize. Right. So after some new. Okay, and so this is the new we take. Exactly same as in L1 stock. And then the point is that each time you will have something which actually lies in this support for large enough nu, then you can actually cook up some abelian subvariety. So this is that if Vs actually belongs to P nu x nu intersected with S nu 0, so which is an element which is in the image of one of this guy at the stage nu in the jet space, then this will yield a subvariety. Will it just so this guy is then an element in the projection of VA, and this guy is in S, and then you can look at the one parameter subgroup of A. So the one parameter subgroup such that f prime of nu is equal to f prime nu of 0 is equal to nu to V. F prime V of 0 is equal to V. And this will actually give you the closure of this. Will be an abelian subvariety, which is actually contained in XS. Yes. So this is just exactly what the L1 explained. Somehow we fix S. This doesn't even play any role now. And then you just look at what happens. So these are somehow some really some horizontal thing in the abelian variety. And not only do you have this, but you also have that but you also have, by the same argument, and for any A in the support of x nu S, so S is, sorry, it's not S here. So here we write, yeah, for this point here, write E S. Okay, so so for any point, if you have something like this, for any point above this point in the fiber, you will also get that A plus B nu will actually be V, will actually be included also in excess by the same argument. And this will actually imply that A plus B V is actually also included in by lifting X nu V S. So for any A in here. And so this exactly will tell you that this guy is actually included in the stabilizer of X nu above the S. Okay, so this is somehow the upshot of all this argument is this. This is what we will actually need. And and now how do you actually conclude? Is so the conclusion is that if you take Vs, so if you take if T the connected components of T intersected with this guy, such that of T nu, such that T intersected with this guy 0 is non-empty, then what I said here is that we'll have an element which is in T intersected with S nu 0, which appears here, right? And so you can apply this construction. And so, anyway, so let me first say that, so we may assume that T is actually irreducible. So here I took connected components, but it's not important. And so if it's irreducible, this will actually yield a map by restriction of the projection, which goes from X nu T to T. And so this map, because we also Hilbert polynomials of X nu above as the fiber of T are constants, which are the maximal possible Hilbert polynomial, this guy is flat. And now the claim is that the stabilizer, or at least connected component containing the identity of the stabilizer of X nu T is independent of T in T. So that's a claim. And once you have the claim, it's actually very easy to conclude, because if so how to conclude afterwards, then this write it denoted by B, and which is different from A. It is different from A by assumption, because I actually supposed that none of the fiber, so this was one of my assumptions, is actually the entire abelian variety. And so this means that this guy is also always different from, all right, yeah. And so, yeah, so I think, I don't apply this, but yeah, it comes from the assumption in for a reason I forgot now, but yeah, it comes from the assumption. And this implies that for any v s in T intersected with S mu 0. So I recall what I want to prove is that T intersected with S mu 0 is actually included in the projection of the tangent space of B times S. So this has so I have to prove that V is actually tangent to B. That's the goal of the proof. And so for all of this, what I have proven here is that BV is in the stabilizer here. Imply that BV is in the stabilizer of X mu Vs, right? But it is actually in the connected component, so containing 0. 0. And this is actually equal to B. And so we proved that BV is included in B, but since the tangent BV is generated by somehow this vector V, this implies that V belongs to B, and so this proved. And yes. Okay, so that's a part. And so I should mention here that I am cheating a bit by saying that actually the stabilizer of this is independent of T. So in fact, this would be true if X mu is irreducible, but it doesn't have any reason to be irreducible, or the restriction of X mu to T is irreducible. So if it's not irreducible, then you first have to throw away also lower dimensional component, and then just work with the maximal dimension component, and then to do some arguments component by component. But yeah, let me just state this in a wrong way, but maybe a bit more understandable. Right. And so if you want to prove the claim, it's actually, from my understanding, the claim is really just some dimensional argument. So the proof of the claim. So if you take any for any sigma variety, sigma, and for any S, say in or let me take Z, I call it Z here. For any Z in A times sigma irreducible, such that the induced morphism Z to sigma is flat, you will have that the stabilizer of Z S is independent of S. And so the idea is actually quite simple. Maybe just some dimension estimate. So basically, the idea is to say, okay, you take the stabilizer of one of the fiber, and you want to prove that it is the same everywhere. And so then what you do, you take the stabilizer and you quotient by your stabilizer. And if ever this stabilizer would not be the same in the other fibers, would not be contained, say, in the other fibers, then you would get some dimension which wouldn't drop. And so basically it's just a dimension count when you project onto A over D. So if let me write it like this. So if for S0 in D fixed, and the D being the stabilizer of the S0, So if D is not contained in the stabilizer of the other fiber or the other Z, then the dimension count after A over D. So really, from my understanding, this is really just, so the flatness here is really just, maybe I misunderstood something. It's just that this map has to be, the dimension of the fiber of this map have to be the same. And this is actually what is needed. And I'm seeing that I will be over time, so I try to go a bit faster. And so why? Okay. So now why is this this lemma is the key lemma? Well, not this one. So this one shows you where you have your abelian variety which comes out, and the other lemma gives you the important estimate. And so let me now show you how you can deduce the result from this estimate somehow. And so I will introduce a notation to simplify. So if you have omega 1 form on D, then I will just denote, so this is the integral and S in 1, 0 and 0, 1. So this was the integral which always appeared in L1's talk. And so I will give it the name. I will call it, so usually you would put the over T here, and you would call this T, say omega R. And maybe if you want to emphasize S, maybe something like this. But this is not actually what Yamano uses. What Yamano uses, for a reason which I still don't understand why he uses this, he uses a non-weighted thing. And so I will call it, give it a name. I will call it Y S R. So, and so I really don't see why he uses this, because simple remark, the point will be to estimate this guy here. So as I want to explain it, because we can compare it with what we want in some situations. But just that if omega is bigger than 0, which will always be the case in our situation, you can just have, you have for any t between s and 1, you have that 1 over t is bigger than 1 and smaller than 1 over s. And then you just get that y omega sr is smaller than t omega sr is smaller than 1 over s y omega sr. So basically to bound this is equivalent as and to bound this. Really, it's really still one of the main mystery in this paper for me is why you actually need this non-completed thing. But anyway, yeah. It's over t here, yeah. So and so he just uses this, but this is if you have this, you have the Jensen formula, and so it's much simpler somehow because you can really work with it as a degree function to some extent. But this you don't have it, right? And so this is somehow much more difficult to work with. But this is what he uses, and yeah. A bit. Maybe I should try to rewrite his entire paper just using T to see. I didn't have the courage to do this. There are many estimates, but anyway. And so the proposition, the main proposition of which you somehow obtained by integrating the previous thing. So you suppose that you have a abelian variety of dimension 0, and S, smooth projective. And you have X in A times S, a closed subscheme, such that, again, for any S in S, XS is different from A. So we will be able to apply the previous lemma in this situation. Then there exists B1, Bm included in A, abelian subvarieties. Such that for any 0 S between 0 and 1, and for any epsilon bigger than 0, and for any delta bigger than 0, there exists C1, C2, C3 constants, positive constants, such that for any f in a holomorphic function from D to X, one has. So you have this bound here. You have the minimum between 1 and m, so over all those abelian subvarieties of the counting function of P, B composed with F, A. So I write F is equal to FA, Fs, right? Because we are in a product. Star PB star of omega A over B I is smaller than epsilon times y FA star omega A, that's R, plus, so you just really should think of this somehow of characteristic functions as R plus C2 times the maximum between 0 and log. A bit complicated, but S with pi plus some constant here. And here, by this I means the inequality holds for all R in S1 outside a set of Lebesgue measure in smaller than delta, right? Of course, if you have entire curves, this will always mean that it's outside a finite set of finite Lebesgue measure, but this doesn't make any sense if you are already just between S and 1, which is a very small set. Okay, and so I will just give you an idea in a simplified case. So you suppose, so you take mu as in the lemma, and suppose that actually P nu, so we have the set T subset nu, which is a set where all the fibers are of maximal Hilbert polynomial, and we suppose that this is everything. So this is exactly a flat family. So this is it's a simplified case, but it's I guess a key case, and this implies that f from D to X lifts to X nu, and therefore P nu lifts P nu composed with F the D is included in P. Okay, and so from the lemma the lemma tells you that if you have any component and you have a small neighborhood around this component for which you have a good estimate. But this will be, we can directly apply this estimate here because the lift of the disk actually lands in T nu. So in particular, it lands in the lift of T in the neighborhood of T nu. And so we just have a lemma. So write T1 PL, the connected component of T nu, and we can apply the lemma, which is B1 BL subvarieties of A, and you can apply the lemma. But those boards are like 40 centimeters too low. I don't know exactly why. And which tells you that you will have for VE star nu VXA omega A over EI squared smaller than VXA squared omega A plus some rho 2 VX. Maybe I should write I, rho I here. X nu squared omega A2, which for all relevant derivative here, and so by pulling back this inequality onto your disk by Fk, this will tell you that and integrating, so you pull back and you integrate with, so you have this double integration and you apply y, basically, operator y. Then you have this is smaller than, so I don't write the pullbacks. So by here, I mean y f star bb I composed with f star of omega a over bi. I simplified using this notation. A s r plus rho I y s nu. So the characteristic function on the, so here's, I should write at least A over B. Yeah. In the quotient is smaller than this A and this nu s here. And this is smaller by a variation of the tautological inequality. So here somehow you should think of this as a counting function of an O of 1 on the news power stage of the template jet space. It's not exactly this, so you have to have a variation of the tautological inequality. And which will tell you that you have, it's really smaller than this, plus some other constant, and you can actually bound this by the one on S. And then you just take rho is max of the rho I, tilde, and this, and you take the min, and you will get that the min of A over Bi SR is smaller. And so here, yeah, I should write, when you apply the tautological inequality, you have some exceptional set that appear, plus, and when you apply tautological inequality, I should have added it here, you actually get some terms here. We call it C I times the max of 0. Plus some other constant maybe, gamma I, yeah. And so you get some constant. Maybe I will stop keeping track of this. I plus some other constant. Okay, and so this is exactly, in a slightly simplified notation, exactly what I have here, right? It's the same thing. If this is not flat, so this is actually the main key technical difficulty of the paper, and it involves many other ideas. So actually, the point is that if ever you don't have this inequality, so if you have an inequality here, then you have to blow up. You can find a suitable blow up such that the maximal Hilbert polynomials on the blow up, if you somehow look at the induced family on the blow up, the maximal Hilbert polynomial drops, and then you can do some induction on actually the maximal Hilbert polynomials that appears in your family, and it's actually very technical to when you apply this induction, I have this upstairs, and then you want to pull back the information before the blow up, and this is actually very technical, really. So, and it involves quite some other idea, because you have to, in a very subtle way, to understand how to relate the functions. Say the characteristic functions on the blow up with the characteristic functions downstairs, and so it really involves some more estimates. And so, just how to conclude from the main proposition. So, what you actually prove, one proves. One has to do another induction on the dimension of the abelian variety, and so you take B times C, B C abelian variety, which are possibly trivial, and Y included in B times C, so a subscheme, or yeah, if here maybe a subvariety, like a subvariety, and you take Y in U open such that the spatial locus of Y, which is all the subvarieties, abelian subvarieties of Y, is included in U. And again, so the point is to prove that pretty much you want to prove in some particular situation that Y is tot modulo the spatial locus. And then for any f between 0 and 1, and for any delta bigger than 0, there exists gamma 1, gamma 2, gamma 3 bigger than 0, such that for any f from B to Y, such with f ds not included in U, one has that Y fb omega b as r smaller. So the natural counting function on B is smaller than some constant time by fc omega c r plus gamma 2 log plus of 1 over f prime 0 omega b times c plus some other constant. And again, yeah. And again, so why does this conclude? This proposition implies the theorem. To prove this, you just have to apply this result with B being equal to A and C trivial. If B is equal to A and C is equal to 0. So this implies that for any f, so you have y just included in A, and this implies that for any f R between S and 1, such that this holds, you will have that the derivative of f prime with respect to omega will be smaller than 1 over p s squared r minus s y fa omega s r. So this is what everyone explained yesterday. It's just a harmonicity, subharmonicity of the square of this function here, of this function. And so you can then bound it by this, but here, if c is equal to 0, this will be equal to 0. You just get gamma 2 log plus 1 over f prime 0 omega l plus gamma 3 times this constant here. And so this implies that f prime omega a is less than some constant c, which is independent on f. And so this is exactly what allows you to conclude. Oh, okay, now I'm already done with my time. Maybe, yeah. Okay, maybe I take 5 minutes if that's okay with all of you. You're stuck here anyways. And so, yeah, and yeah, okay, maybe try to be quick. So the idea of the proof. So again, is that so it's an induction on the dimension. Dimension of B, and so if dimension of B is equal to 0, it's trivial, right? So the left-hand side is equal to 0, and you don't have anything to say. So now suppose that dimension of B is bigger than 0, and that it holds for all lower dimensional, and proposition holds for all B prime in B. So again, we take y in B times C and assume for simplicity, so which is not, you cannot always do, but that ys is different from B for all S and C. And the main proposition will imply that there exists B1 Bm in B such that you have the minimum between 1 and m of the counting function of the different quotients is smaller. Let me just even write it a bit. C2 times the max of 0 and the integral of log 1 f prime s I e theta d theta over 2 pi plus C3. And what you actually prove then what we prove. This will imply and somehow to get actually so you have this and somehow to get the bound you want. Here you want to bound B with respect to something, and you know how to bound all the BI. So basically what you will prove that for each BI you can actually bound B, the counting function with B, with something involving the BI. And we will prove that for any you have a counting function with respect to B is smaller than, let me just write some constant, time the thing with respect to B plus the quotient plus some other constant times log plus of 1 of f prime of 0 plus some other constant. And so with this, 2 star will just imply plus the main proposition. This estimate here will just say that if you have this for all BI, up to changing the constant, you will have this for with the minimum here. And you can substitute this here with the minimum here by what you have here. And you can actually compare. The point here is that this guy here is actually smaller, again, by the subharmonicity argument, which was explained by R1, is smaller than this guy here. And then you just have to put everything together, and it will give you that y, well, exactly what you want, actually, that yb is smaller than, outside some exceptional set, some constant, time yc plus some constant time log plus of 1 of f prime 0 plus some constant, which is the thing here. And then you just have to prove 2 star. This is where actually I think I just wanted to say this because it's actually somehow an interesting thing is to prove 2 star. Yeah. Double star, which is also an idea that appears in several of the work for hyperbolicity and nonlinear theory in abelian varieties, is to say that for any I between 1 and m, you have bi, which is so bi times 0 included in b times c, and you can look at ci, which is b over bi times c, and by Poincaré reducibility lemma. This is one of the other main ingredient here. Theorem. So there exists a commutative diagram, bi times ci to iota b times c to ci to ci and kappa here. And so here you have isogenies. And then basically, but here the dimension of bi is strictly smaller than the dimension of b. And because the dimension of bi is strictly smaller than the dimension of b, this tells you that you can apply the lemma for in this variety. And so here you have and here you have y. And so here you have y tilde, which is just the lift of y, because it's étal. And because this map is étal here, pretty much all the thing you can compare all the relevant counting functions, and then you can just deduce the thing which you obtain here. Well, the thing you want here from the thing you obtain here, just by some estimates. Which I won't do. Sorry for this. Thank you very much. you have any questions? It was